Okay, today we are going to cover section 4.4, which is on solving exponential and logarithmic equations. So let's take a look at our first example. We have equations that have just one logarithm, and that's what you see on the screen here. With logarithmic equations, it's important that you check your final answers in the original equation. It's possible to get extraneous solutions, which are solutions that really don't work in the original equation. So we have to check our answers on all of these. For solving an equation with one logarithm, it's a pretty simple process. We're just going to do the loop and convert it from logarithmic form to exponential form, just like we were doing earlier in the chapter. The equation we have on the board right now is log of x plus 20 equals 2. So remember that if the base is not specified, we are to assume it is base 10. So we have log base 10 of x plus 20 equals 2. All right, and we want to solve this equation for x. We'll do the loop to convert it to exponential form. Remember how the loop works? We start with the base of our logarithm, which is 10. We raise it to the power of whatever's on the other side of the equal sign, which is 2. And then we set it equal to whatever's inside the logarithm, which in this case is x plus 20. Now we have x outside of the logarithm, out in the open, where we can actually solve for it. So we'll go ahead and simplify the left-hand side. We have 10 squared, which is 100, equals x plus 20. And it's a very simple, nice, linear equation. Solve for x by subtracting 20 from both sides. And we get that x is equal to 80. We should double check to make sure this solution is valid by plugging it back into the original equation. And so we will check our answer, but I'm pretty certain that it works out fine in this case. Usually if there's just one logarithm, there's not really a problem. It's when you have multiple logarithms that you really need to be careful about the answer that you get. But let's just, for the sake of following through with what I just said, let's go ahead and check our answer. So we're going to take x equals 80. We're going to plug it into the original equation. We have log base 10 of 80 plus 20, right, equals 2. Pardon me, I'm just going to write it down there a little bit on the next line. So we simplify 80 plus 20 is going to give us 100. So we get log base 10 of 100 equals 2. And remember what a logarithm is. It's asking how many powers of the base does it take to equal the thing inside the logarithm. So in this case, we're asking how many powers of 10 does it take to equal 100? The answer is 2, and so the equation is satisfied. All right, moving on to the next example. Let's take a look here. Oh, sorry, we weren't supposed to see the wizardry behind the magic here of recording my lecture. This is what you were supposed to see. Here we go. All right, so let's go to the next example. This one's a little more complex, but we're really going to be doing the same thing as we did on the previous example. So again, the base is not specified, so we are to assume it's log base 10 of x squared minus 15 equals 1. And we'll do the same exact thing that we did on the previous example. Keep in mind on the test, a common mistake that I see is that students do not do the loop. They do, like somehow they just get x squared minus 15 equals 1. And so be careful not to leave that power of 10 out, or sometimes they'll get it backwards. They'll do 1 to the 10th power instead of 10 to the first power, which is what we should do here. You start with the base of your log. You raise it to the power of whatever's on the other side of the equal sign, which in this case is just 1. And then you set it equal to what's inside the logarithm, which is x squared minus 15. Right. 10 to the first power is just 10, so we get 10 is equal to x squared minus 15. This is technically a quadratic equation. We could solve it using the quadratic formula, or in this case, since there's just the one x in the whole equation, there's just this x right here, we can actually just solve it for x, which I think is going to be a little bit easier. So let's go ahead and do that. We'll add 15 to both sides. We get 25 is equal to x squared. And then we take the square root of both sides to solve for x. Remember, this is the danger of just solving it for x because it's easy to forget. But when you take the square root of both sides, you have to do plus or minus. So we won't just get 5 here. The square root of 25 is 5, but it'll be plus or minus 5. So we really have two solutions. Right, we have x is equal to positive 5, x is equal to negative 5. And then we should check to make sure that these both work, but I'm going to be a little bit lazy here. So I'm going to say what you should do, but I'm not actually going to do it myself. You should check to make sure that these solutions actually work in the original equation, but they actually do, both of them. So they're both valid solutions. If you plug it back in, you can see that for yourself. Even the negative one will be okay because when you plug it back into the original equation up here, when you square that negative value, it still comes out positive. So if you plug in positive 5 up here, you're going to get 5 squared, and I'm talking about up here at the top right here. If you plug it in right there, you'll get 5 squared, which is 25. 25 minus 15 is 10, and then log base 10 of 10 is 1. Right? How many powers of 10 does it take to equal 10? So what you'll get when you plug 5 in to the original equation, I probably should have just went ahead and checked the answers. It would have been quicker than me talking about it, but if you plug in 5 here for x, you'll get 10 as a result. Log base 10 of 10 is 1, so it works out. And the same thing happens with negative 5, because when you take negative 5 squared, you'll get negative 5 squared, which is also positive 25. 25 minus 15 is again 10, and log base 10 of 10 is 1. So they both work in the original equation. All right. So that's how you handle equations that have just one logarithm. The example number 11 here is a little bit unusual because the base is where your variable is located, not inside the log, but the actual base itself. But you actually just solve it the same way. You just do the loop. So I'm not going to bother to do that example. Let's move on to, and you won't really see it. It's very rare. This is a very uncommon example. So you shouldn't see that on your homework, really. Let's look at equations with 2 logarithms. You will definitely see these on your homework. But these really are no more challenging than the equations with 1 logarithm, because what we're going to do with these 2 logarithms is we're going to add them together into a single logarithm. We talked about how to do that in the previous section, right? We can add logarithms together into a single logarithm. We can contract them into a single logarithm. And when we do this, we're going to write a single log. The base will stay the same, so it'll still be base 2. And then inside of that single logarithm, what are we going to do with the x plus 2 and the x minus 2? We will multiply them together. And why are we going to multiply them together? Because the logs are being added. That's the weird behavior of logarithms. We can add logarithms into a single logarithm by multiplying what was inside the individual logarithms together. So I'm going to have x plus 2 being multiplied to x minus 2 inside of this single logarithm. And it's still going to equal 5, right? The equation is still equal to 5. So that's the first step. If you have more than one logarithm, contract them down to a single logarithm using the rules that we learned previously. If you're adding the logarithms, you will multiply the individual arguments together in that single logarithm. And then we will do the loop again. So we'll start with the base of 2, right? It's not going to be 5 squared. It's going to be the base is 2, and raise that to the 5th power. So we're going to get 2 to the 5th power equals what's inside the logarithm, which in this case will be x plus 2 times x minus 2. All right, so what are we going to do here? We're going to simplify. We will first need to do the exponent. 2 to the 5th power is 32. On the right-hand side, we will FOIL, and we're going to end up getting x squared minus 4 when you FOIL that out. So I'm going to leave that little bit of detail out, but foiling at this point should be something that you're pretty comfortable with, and you should be able to fill that detail in for yourself. And again, we get a quadratic equation, but it's of the simpler variety because we can actually just solve this for x. There's just one x in the whole equation, so let's get that x by itself. We'll start by adding 4 to both sides. We're going to get 36 is equal to x squared. And then we will take the square root of both sides, and we're going to get plus or minus 6, right? Remember, when you take the square root of both sides, you have to do plus or minus. And so we get 2 solutions again. We get x is equal to positive 6, x is equal to negative 6, just like we had in that last equation. But in this case, we really need to check our answers. If you start with 2 logarithms in your equation, you definitely have to check your answers. There's no safety there at all. So we have to check these answers, and it turns out one of these doesn't work. Which one would you guess is the one that doesn't work? If you guess the negative one, you guessed correctly. So you should check both of these. So let me say that, but I'm only going to check the one that doesn't work, again, in the interest of time. So you should check both solutions, but let me just go ahead and check x equals negative 6 to show you that this is the one that doesn't work. If you check positive 6, it works out fine. All right, so let's check this solution. You have to check it in the original equation. So you want to go back to the original equation before you combine the logarithms together. So back to when we had this. Log base 2, I can't quite remember what the first one was. It was x plus 2, it looks like. So log base 2 of x plus 2 plus log base 2 of x minus 2, and that's supposed to equal 5. All right, so again, I'm trying to squeeze it into this little area here, so I apologize that it's not all on one line. And we're going to plug negative 6 in for x. So here we're going to plug in negative 6. Here we're also going to plug in negative 6. And so what does that look like? We're going to have log base 2 of negative 6 plus 2 plus log base 2 of negative 6 minus 2 equals 5. Right. And this isn't going to work because we will end up with a negative number inside the logarithm. Right. So what we end up with is log base 2 of negative 4 plus log base 2 of negative 8. So both of them cause a problem, equals 5. And the reason this is a problem is because you can't take the logarithm of a negative number. It doesn't matter what the base is. If the number inside the logarithm is negative, it doesn't work out. So this has no solution. This has no value to it. It's impossible. We've violated the domain, right? We plugged in a negative number into a logarithm. That's against the domain of that function. It doesn't know how to operate on that kind of number. So there's no value for log base 2 of negative 4. Same thing with log base 2 of negative 8. So it doesn't satisfy the equation because it doesn't give us any numbers to work with. Right, so negative 6 has to be thrown out. If you check positive 6, it actually works out fine. If you want to, maybe we could do that real quick just by erasing the negative sign here and see what happens. Right, so let's erase that negative sign. We're going to plug in 6 for x. We'll end up getting 6 plus 2 in the first logarithm and then 6 minus 2 in the second logarithm. Right, and so what we end up getting is log base 2 of 8. Right? This will be log base 2 of 8. This will be log base 2 of 4. Right? 6 plus 2 is 8. 6 minus 2 is 4. And these work out just fine. Right? Log base 2 of 8, how many powers of 2 does it take to equal 8? The answer is 3. Log base 2 of 4, how many powers of 2 does it take to equal 4? The answer is 2. 3 plus 2 is equal to 5. So it works out when you choose x equals 6. It doesn't work out when you choose x equals negative 6. All right, good. So that is how equations of two logarithms works out. I only have the one example of that. The other one that you saw on the screen is, again, a little bit unusual because everything is a logarithm in that case, and I don't think you're going to see that kind of problem on your homework. I used to put those unusual ones on the homework, but even if I happen to put one on the homework, you're not going to see one like that on the test. And same thing with 25. It's really just more unusual. If we have time, I don't want this video to go over 50 minutes. So if we have time, we'll come back and look at one or two of those. Let's take a look at something more typical, something you definitely need to know how to do for the test. Equations with just one exponent. So we have 2 raised to the x minus 1 power equals 7. All right. So how do we solve this equation? There's a couple of ways you could go about doing this. The first thing you have to decide is, do you want an exact answer, which would involve keeping the logarithms in your answer, or do you want an approximate answer? And I think in this case, what we will want is an approximate answer. The direction should indicate this. It's not really up to us. The direction should say, find the exact solution, or the directions will say, round your solution to 4 decimal places, which in that case means we want an approximate solution. So if we want an approximate solution, we need to use a logarithm to solve this equation, and we need to use one for which our calculator can compute it. So most calculators don't have a way of doing log base 2 or log base 5. Most standard calculators, at least this is how it used to be 5 or 10 years ago, only had log base 10 or natural log, and so that's what we're going to use to solve this equation. So I'm going to apply, so if you're trying to solve, let me start with this. If you're trying to solve with a variable, if you're trying to solve for a variable that's in the exponent, like x is right here, you need to use a logarithm to accomplish that. And we can use log base 10 if we want to use that. That way we can plug it into any calculator. The way we use the logarithm is we apply that logarithm to both sides of the equation. So I'm going to apply a log base 10 to the left-hand side of the equation. I will apply a log base 10 to the right-hand side of the equation to balance that out. All right, so we apply a log base 10 to both sides. Again, I don't have to actually write the base in this case because the base is 10, so we don't actually need to write that. So what does this allow me to do? The logarithm has another rule that we haven't used yet today, on this video anyways, which allows me to take any exponent that's inside the logarithm and multiply it down in front of the logarithm. It's called the power rule for logarithms. Right, so I can take the x minus 1 because everything in here is being raised to that power, and I can multiply it down in front of the logarithm. So I'm going to bring the x minus 1 down to the ground, multiplied in front of this log base 10, and the 2 will be left behind in the logarithm. But it gets the x out of the exponent down to the ground where we can solve for it. The right-hand side, nothing's going on there yet, so I'm just going to copy that down. So now I can solve for x. We just have one x in the whole equation. In order to solve for x, I have to get it out of the parentheses that I've trapped it in here. And so to get rid of the parentheses, there's a couple ways you could do this. I'm not really sure what the best way is. I don't know, I guess the easiest way would be to divide this log base 10 of 2 to the other side. It's being multiplied to the parentheses. So to get rid of that logarithm, we will divide by it on both sides. And if you get rid of the logarithm, you don't need the parentheses anymore. Right? So that's why we're going to get rid of the parentheses. So we'll divide by log base 10 of 2 on both sides. It'll cancel it out from the left-hand side. And so we'll end up with x minus 1 on the left-hand side, and it doesn't need parentheses anymore, equals log base 10 of 7 divided by log base 10 of 2. Now this wasn't the only way to get rid of the parentheses. We could have distributed the logarithm into the parentheses, but it gets even more messy if you do it that way. But whatever way you're comfortable with would be fine. It'll look different depending on how you do it, but we'll get the same answer either way. So now to get x by itself, we'll just add 1 to both sides. And so I get x equals log base 10 of 7 over log base 10 of 2 plus 1. So I need to use a calculator, so let me see if I can find one here. Okay, I think I have one here. So we'll do log base 10 of 7 divided by log base 10 of 2, then add 1 to that answer. And what I come up with, hopefully this is right, 3.8074 if you go to 4 decimal places. Again, this is an approximate solution. So the initial result that we got is an exact solution. It's maybe not in the best form. It's in log base 10. We got a fraction there, but it's an exact solution. When we plug it into the calculator and get a decimal for it, it becomes an approximate solution. All right, so that's how you solve an equation that has just one exponent. You apply a logarithm to both sides. It lets you bring the exponent down to the ground, and then you can solve for x from there. All right. Let's see. Number 31 would work in a very similar fashion. In fact, it'd be even easier because the exponent's simpler. So I'm going to go ahead and skip that one. And again, if we have time, we can come back to that. Let's look at an equation with 2 exponents. These, while they look pretty friendly, they're pretty simple and unassuming, are some of the toughest ones to solve because you'll have a lot of logarithms to deal with. So let's take a look at this equation. We have 6 to the x power equals 3 to the x plus 1 power, and we want to solve that for x. So we have 2 exponents that are in this equation. So what we'll do, just like in the last problem, to get those x's from the exponent down to the ground, we need to use a logarithm. Because we want to be able to plug it into our calculator, we'll use log base 10 on both sides. So I'm going to apply a log base 10 to the left-hand side of the equation and a log base 10 to the right-hand side of the equation. Excuse me, I need to get some water there real quick. Okay. We use that power rule that we used on the last example to bring the exponent, multiply it down in front of the logarithm. We'll do that on both sides of the equation. So all of the x's get brought down to the ground where we can actually then solve for them. So what we're going to get is we will get x times log base 10 of 6 equals x plus 1 times log base 10 of 3. Now this one we can't really use the trick we used in the last example of just dividing the logarithm away to get rid of the parentheses on the right hand side, because we also have an x attached to the logarithm on the left hand side. So this time we're going to have to do it the other way I kind of alluded to in the last example. To get rid of the parentheses on the right hand side, we will need to distribute the logarithm into the parentheses. Right, so the left hand side I'm not going to do anything with at the moment. I'll just leave it as x times log base 10 of 6. On the right hand side, we're going to get x times log base 10 of 3. So the log base 10 of 3 gets multiplied to the x. And normally if we distribute a number into a parentheses, we put that number in front of x. But logarithms we tend to leave behind the variable. We try to keep everything in front of the logarithm for each term. Right? And then the log base 10 of 3 gets multiplied to the 1. So we'll get 1 times log base 10 of 3. Of course, 1 times anything just leaves it as it is. So we got the x out of the parentheses. That was the first impediment to solving this equation for x. The second impediment is that we have x in two different places. You can't solve an equation for x while it's in two different places. So what we need to do is bring all the x's together on one side of the equation. So I'm going to bring this x log base 10 of 3 over to the left-hand side by subtracting it over there. It's a term, so I will subtract it over to the left-hand side. All right, so it's going to look like that. And then we will do a little trick, and we will get it solved for x. Hold on, sorry, I apologize, that showed up on the screen. Let's try that again. Okay, so what we're going to end up with is x times log base 10 of 6 minus x times log base 10 of 3 equals the thing that's left over on the right-hand side, which is just the log base 10 of 3, which came from here, right? This thing, right? We didn't do anything with that, so we copy that down. All right, so usually I kind of torture my class with this question about what should I do next. I have x log base 10 of 6 minus x log base 10 of 3. I have two x's still. How can I make one x out of these two x's? And I usually wait in silence for a couple minutes for people to think about it. And half the time somebody figures it out. The other half of the time I have to tell my class. So I'm just going to have to tell you guys, since this is a video and I can't wait for you to figure it out. Of course, you could just pause it and think about it for a minute. And what you should come up with, hopefully, is you have to factor out the x, right? We have two terms here. X is a common factor in both of these terms. So we can factor out the x. And what happens when you factor out the x is you write it one time out in front. And so you go from having two x's to just having one x, right? So we're going to factor out the x. Factoring out is like undistributing it. We're going to bring the x out in front. We write it one time in front. What's left over is a log base 10 of 6 from the first term minus log base 10 of 3 from the second term. The right-hand side didn't change, so I'm going to copy it down. All right. Good. Now we have just one x. How do we get this one x by itself? Well, it's being multiplied by this parentheses. So to get this x by itself, I will divide by that parentheses. I'm going to divide by log base 10 of 6 minus log base 10 of 3. And we could have simplified this a little bit before we divided by it. I'll go back and show you that trick here in just a minute. All right, my pen's starting to act up again. This board is getting kind of old, so log base 10 of 6 minus log base 10 of 3. I didn't really need to keep parentheses around this thing, but I did. All right, so that's going to cancel this out, right? The log base 10 of 6 minus log base 10 of 3 cancels out. On the left-hand side, we get x by itself, which is what we were trying to do this whole time, equals log base 10 of 3 over log base 10 of 6 minus log base 10 of 3. Now when I'm writing it on the board, I don't need to put parentheses around the denominator, But when I go to type it in my calculator, I definitely do. So maybe it is a good idea to keep this in parentheses, because when you type it in your calculator, you will need to use parentheses on that denominator to get this answer. So let's practice typing these in our calculator. Make sure you get the same thing I get. So I get log base 10 of 3 divided by parentheses log base 10 of 6 minus log base 10 of 3, close the parentheses, and I end up getting x equals 1.5850 if you round it to 4 decimal places, which is usually what the book asks us to do. All right. Now the shortcut that I was alluding to, which would have made this a lot less messy, is if you go back to here, let's see, to this part right here, we're subtracting 2 logarithms, and we learned about this rule earlier in the chapter. When you're subtracting logarithms, they can be subtracted into a single logarithm, a single log, by dividing what was inside the original logarithm. So I'll take 6 divided by 3, and this becomes log base 10 of 2. So then my equation would look like this. Where can I write it at? It would look like this. I'm going to show you down here. It would look like this. I'd have x times log base 10 of 2 equals log base 10 of 3. And that's a lot cleaner than the way we did it, right? So we could have combined those logarithms together into a single logarithm and then divided by that single logarithm on the other side. And we would have got the same answer, right? We would get 1.5850. All right, so then you would divide by log base 10 of 2 on both sides. So it's not necessary to have to do that, but it would have been a lot neater looking if I had. All right, so that's how you solve an equation with 2 exponents. As I said, the equation initially looks very simple and unassuming, but once you start digging into it, it does become fairly complex. Now I do want to do this second example here, number 39, because whenever there is a way out of what we just had to do, we definitely want to take it, right? So in this case, it's the same kind of setup. We have 2 exponents. 2 to the x minus 1 power equals 4 to the 3x power. And you can certainly solve this equation the same way. You could, apply a log base 10 to both sides and bring the exponents down to the ground and go through all that, just like we did on the last example. But there's a much easier way to do this problem. So always be on the lookout for this shortcut. And this is a shortcut that we talked about way earlier at the beginning of the chapter. And that shortcut is, if you can get both sides to have the same base, then you could just set the exponents equal to each other, and you don't even have to use a logarithm. This is how we solve these equations before we even talked about logarithms, but it only works if both sides have the same base. We would have loved to do that here for this previous example, but there's no way to get 6 and 3 to have the same base. Right? There's no easy way to do that, right? And so we were stuck using logarithms to solve this particular equation. So don't think that you could have done any problem this way. The bases have to be such that they could be made the same, and that wasn't possible for number 35. So you have to use logarithms sometimes. But here's a case where we don't have to use a logarithm, because the 4, we can write that with a base of 2. And if you can get both sides to have the same base, then you don't need logarithms. Right? So 4, we can write that as 2 squared. So now both sides have the same base, but we have to be careful here because this 4 is getting raised to the 3x power. So when I go to rewrite it as 2 squared, it still needs to get raised to the 3x power. Right. On the left-hand side, I'm not doing anything with that, so I'm just going to copy that down. But now we have the same base. Before I go to set my exponents equal to each other, I should probably simplify the exponent on the right-hand side. And when you have one power being raised to another power, what do you do in that case? You multiply the exponents together. So you're going to get 2 to the 6x power. 2 times 3x is 6x. And now I can use the shortcut because these have the same base. The only way this equation could be true is if the exponents are equal to each other. So all I'm going to do is set x minus 1 equal to 6x. I'm not canceling out the 2's, even though you could do that if you used a log base 2 on both sides, but I'm just bypassing the whole exponential equation, using this little loophole, which is if you get the same base, you just set the exponents equal to each other. And then you solve that equation for x. So I'll subtract x from both sides. I get negative 1 is equal to, sorry, it's not 6, it's 5. 5x. All right. And then we divide by 5 on both sides. And we get that x is equal to negative 1/5. And that's it. So pretty easy. No logarithms at all. So always be on the lookout for that. On the test, it kind of randomly generates numbers, and every once in a while, when I intend for the problem to be the hard way, with logarithms, it sometimes randomly generates these numbers where you can use this shortcut. So always be on the lookout for that. It saves you time and saves you headache. All right. Okay, so this miscellany problem here, one of my favorite equations. If we have time, we'll come back to that one also. But it's definitely above and beyond anything that you really have to be able to do, so it's really optional. I'm not going to bother doing that one. And 47 is pretty tough. We'll come back to that too if let's see if we have time. So what I would like to do is some word problems. Let's see. Well, maybe I won't. Let's see. I don't have them typed up on here, so maybe I will go ahead and go back to these equations I skipped earlier and finish those out. And then we'll save the word problems for Wednesday, for class on Wednesday. And I don't know, maybe I'll do a separate video for word problems to post on YouTube. All right, so let's go back to some of these ones that I skipped earlier. Let's see. Let's go ahead and do this one. This one's probably the most relevant to word problems anyways. All right. So solving this equation is pretty tough, and this one's more likely to show up on your homework, I think, than the other equations I've skipped. So we have 4 times 1.02 to the x power equals 3 times 1.03 to the x power. I'm wondering if this is possible. I don't know. I guess with the same exponent, yeah, I guess maybe it's possible. Okay. Seems like I wonder, like, is there a number, because x has to be the same number on both sides of the equation, right? So whatever we get for the solution has to be the same on both sides. And I just wonder if it's possible to get them to be equal to each other when they have different bases. But I guess the 4 and the 3 make that possible. So let's find out. We'll find out by trying to solve it. All right. So again, we're trying to solve for a variable that's stuck in the exponent. If you haven't learned by now, you should learn. You should pick this up right now on this example, and that is if we're trying to solve for a variable in the exponent, we have to use logarithms, right? So we have to use a logarithm to bring that x down to the ground. So I'm going to apply a log base 10 to both sides of this equation. Apply a log base 10 to the left-hand side. Apply a log base 10 to the right-hand side. But we run into an issue with this equation. The issue is not everything inside the logarithm is being raised to the x power. And so the power rule that we had used earlier doesn't apply here just yet. So I cannot take this x and multiply it down to the ground, in front of the logarithm, because the 4 is in the way. The 4 is blocking me from doing that because the 4 is not being raised to that power of x, and so I can't bring this x and multiply it down in front of that logarithm while the 4 is still there. So let's erase that idea. So what we have to do, right, is get the 4 out of the way. So how do we get the 4 out of the way? Well, it's being multiplied to the 1.02 to the x power. And so we can actually split this logarithm up and separate the 4 from the 1.02. Right? And so the 4 will get to have its own logarithm. The 1.02 to the x power will get to have its own logarithm. And I'm not going to use, I guess, okay, I'll go ahead and put parentheses in there. You don't really need the parentheses there anymore. And what do I do with these logarithms? Because I'm multiplying up here, I will add the logarithms together. And we do the same thing on the right-hand side. We'll get the 3 gets to be in its own logarithm, and the 1.03, oh gosh, I'm going to run out of space, to the x power gets to have its own logarithm. I'm not going to use parentheses there because I need the space. All right. The only reason the parentheses are necessary up here is because there's a 3 in front of it, but once the 3 is out of the way, I don't really need parentheses around the 1.03. Now I can use the power rule to bring this exponent of x down to the front. Sorry, I thought I changed the color there. Let's try that again. Down to the front of just that logarithm. It doesn't go in front of the logarithm with the 4. It only goes in front of the logarithm with the 1.02. And I can get away with that because now everything here is being raised to that power. And so I'm going to get log base 10 of 4 plus x times log base 10 of 1.02. The same thing's going to happen on the right-hand side. We'll get log base 10 of 3 plus x times log base 10 of 1.03. We're bringing the x, multiplying it down in front of that logarithm. All right, now from here what we need to do is get all of our x's together, right? We can't solve for x while there's still 2 of them in the equation. So I need to get all of my x's to one side, and any term that doesn't have an x needs to go to the other side. And so what I'll do is I will subtract the x log base 10 of 1.02 over to the right-hand side so that these can be together. And then this term right here that doesn't have an x doesn't belong to this club. It doesn't belong to that group. So he needs to be moved to the left-hand side. So he can be with the guys that don't have an x. I'm going to move him over here. So I'm doing 2 things at once. I hope that wasn't too much to chew at once. So what am I going to end up with? I'll end up with, on the left-hand side, I'll have the log base 10 of 4 minus the log base 10 of 3, right? This part right here. On the left-hand side, I'll have x log base 10 of 1.03 minus x log base 10 of 1.02. Now what we can do to simplify things, I don't know if it's really going to simplify it all that much. We could combine these logarithms together into a single logarithm since we're subtracting. So I can write that as log base 10. And what do I do with the 4 and the 3? If I'm going to write them in a single log, I will divide them, right? So it'll be log base 10 of 4/3. So it's a fraction in there, but at least it's just one logarithm. On the right-hand side, what will I do? The same thing I did on that last example. I will factor out an x, and I'll be left with log base 10 of 1.03, almost put a 2 there, minus log base 10 of 1.02. And let's learn our lesson from that last example. Sorry, there should be another parentheses here. Let's try that again, a little bit smaller, 1.02, like that. All right. So from the last example that we did, we realized it would be a lot cleaner if we just go ahead and combine these logarithms together. Even though it's going to become a fraction and not look very friendly, at least it'll just be one logarithm to deal with. Same thing as the left-hand side. We're subtracting, so I'm going to combine these into a single logarithm by dividing. Sorry about that. Let's try that again. The 1.03 gets divided by the 1.02. Inside of a single logarithm, and we'll just copy the x down in front of that. The left-hand side, we didn't change anything, so we're just going to copy that down. Right. So I think this is a lot easier to see what's going on. Now, to get the x by itself, we just divide by this log base 10 of 1.03 divided by 1.02. We divide that on the left-hand side as well. All right, and so that's how we get our solution. We're going to have log base 10 of 4/3 over log base 10 of 1.03 divided by 1.02. Whoops. Let's get that parentheses up here. Right, and that's what x is equal to. And that's still an exact solution, but we want the approximate solution. So let's plug this into our calculator, our equator. I don't know why I was going to say equator for. Our calculator, we get log base 10 of 4/3. And here I don't really need to worry about using like extra parentheses, just the ones that naturally come with the logarithm, divided by log of 1.03 divided by 1.02. And what you should end up getting is 29.4872. So surprisingly, there is a solution to this equation. It doesn't seem like, initially I didn't think it would maybe even be possible to have a single exponent on both sides of that equation that would make both sides equal to each other, but indeed there is something. And again, this is just approximate down to the 4th decimal place. All right. So that's a really, really tough equation. I might put one of those on the homework just as an extra challenge problem on the homework, but you should not expect one as difficult as this on the test. That would be, I think, asking too much. All right, so let's see, we got about 10 minutes left of this video. Let's go back and cruise for another problem to look at. I don't know, let's talk about this one where everything was a logarithm. There's 3 logarithms in this problem. There's a shortcut to this one. And again, this is sort of an unusual equation. These aren't very common, so you probably won't see too many of these. But we have natural log of x plus natural log of x plus 2 equals the natural log of 8. So what we can do is, and what you want to do with these multiple logarithm problems is condense the logarithms down to a single logarithm if possible. And you could do that by subtracting the logarithm from the right-hand side over and then shrinking all 3 of them down to a single logarithm. That would be the hard way to do it. The easy way to do this is to condense just the 2 you have on the left-hand side together into a single logarithm. You'll get the natural log of x times x plus 2. Right? We multiply these together since these logs are being added. That's why this becomes a multiplication. Right? Equals natural log of 8. And we're going to use the same shortcut we talked about a couple of examples ago. Same idea, basically, here. Right? So the shortcut here was if you get both sides to have the same base, you just set the exponents equal to each other. We can use the same shortcut on logarithms. If you get 2 logarithms equal to each other with the same base, you can just set the arguments equal to each other. So these have to be equal. Right? The only way this equation can be true is if the thing inside the logarithm on the right, or on the left-hand side, which is x times x plus 2, is equal to the thing inside the logarithm on the right-hand side. This shortcut only works if you have 2 logarithms that are equal to each other and they have the same base. The base of the logarithm in both of these cases is the Euler's number, log base e. So this is log base e on the left-hand side, log base e on the right-hand side. So we set these 2 arguments equal to each other. And so we end up getting this quadratic equation, right? So it might not look quadratic yet, but it will once I distribute this x. So we're definitely not done. We still have a couple more things we need to do, but that's the shortcut to doing this problem. If it's quadratic, in this case, since we have 2 x's in our equation, we can't just solve it for x. We're going to have to get 0 on one side and then either factor or use the quadratic formula. That's another possibility. Thankfully, in this case, it is factorable. We can factor this as x plus 4 times x minus 2. We set each factor equal to 0. And so we're going to get x plus 4 is equal to 0. X minus 2 is equal to 0. And then we solve for x in each case. So now we can solve it for x. We get x is equal to negative 4. And here we add 2 to both sides, and we get x is equal to 2. But remember, if you're solving an equation with multiple logarithms, you have to check your answers. Right? So you have to make sure that these actually work. And so let's double check, and you have to check the original. And again, the negative solution doesn't work in this case, because if you plug a negative number into this logarithm here, if I plug in x equals negative 4, it doesn't work. You cannot take the logarithm of a negative number. And so if I plug negative 4 in here for x, it's the logarithm of a negative number, and so that doesn't work. If you plug in positive 2, that's the solution that ends up working. And you can double check that for yourself. If you plug in 2 for x, it's going to be a little bit tricky because you'll have natural log of 2 plus the natural log of 4. And then you have to add them together. When you do that, you multiply the 2 and the 4 together and you get 8. And so you get natural log of 8 equals natural log of 8. The other thing you could do is plug it in your calculator, right? If you plug in 2 here for x and you plug in 2 here for x, the natural log is another logarithm that's on your calculator. So you could actually calculate that, get the decimal for that on the left-hand side, check to make sure it equals the same thing as natural log of 8 by plugging that into your calculator as well. And you'll see that 2 works, but negative 4 does not. So we have to throw out negative 4, but 2 is our solution in this case. Okay. Got about 5 minutes left, so I think that's probably time for one more equation. Number 25 is a little bit of a trick question. You have logarithms there, but you don't need to condense the logarithms together necessarily because the x is already down on the ground, right? You already have x out in front of it. The x is not stuck in the logarithm. It's not up in an exponent. The x is already out in the open where you can solve for it. You just need to get your x's to one side, factor it out, divide the rest of it to the other side. So it's sort of like dropping you in like the halfway point of when you're solving an equation that had exponents. All right, like I said, 45 I think is just really an extra challenging question. So I think we've done all the equations I really feel like need to be done. So I think I don't know. I really do like this equation. I guess since we have 5 minutes, let's go ahead and do this one. You don't have to watch this if you don't want to, because like I said, this equation is really just a unique equation. You're not going to see one like it on your homework or on the test. But if you have any enjoyment of math, you probably would enjoy solving this equation. So we have log base 10 of z, and that's getting squared, not on the inside, right? The power of 2 is not inside the logarithm, it's outside the logarithm, which means we can't bring this power of 2 down in front of the logarithm because it's not inside the logarithm to do that with. Contrast that with the right-hand side where that power of 2 is inside the logarithm. So there is a difference there between these two. All right, so what we're going to do is actually bring that power of 2 on the right-hand side because it's in the logarithm and everything here is being raised to that power, and multiply it down in front. On the left-hand side, we're not going to do anything with that. We'll just leave it as is and copy it down. So we'll get 2 times log base 10 of z on the right-hand side. And what we're going to do with this, and this is where it gets really tricky, we're going to use substitution. And I'm going to use a variable to replace the log base 10 of z on both sides of the equation, because that's what I have now on both spots. They're both log base 10 of z, and that's a little bit intimidating and complicated and confusing looking. So I'm just going to cover them up with a new letter until I can figure out what to do. And then I can bring it back in later when I've figured out what to do. So I'm going to replace this log base 10 of z with a w. So now instead of log base 10 of z squared, I will have w being squared here equals 2 times, in place of this one, we're also going to put a w. Right? The important thing is that you're just consistent. So whatever you're replacing with a w has to be the same everywhere. All right, so we get w squared equals 2 times w, and I can see, okay, this is quadratic. This is a quadratic equation. How do I solve this quadratic equation? Sorry, I don't know why it keeps doing that. Let's erase that. All right. So how do we solve a quadratic equation? We get 0 on one side, and we have to do it this way because, again, we have the variable in two different places. So we have to get 0 on one side, try to factor the other side, just like we did in the last example. So I'll subtract the 2w over to the left-hand side, so I get 0 on one side, and this is factorable. You don't want to overthink it. All you have to do is factor out a w. Right? So now I was able, by having w in place of that logarithm, I was able to figure out what to do to solve this equation. It ends up ultimately being quadratic, and then I factor, set each factor equal to 0, and so we're going to get w equals 0, and we'll get w minus 2 equals 0. Which means that ultimately w is equal to 2, right? When you add 2 to both sides, you get w is equal to 2. So you have w equals 0, w equals 2. Now, if you type this into your online homework system and say the solution is 0 and 2, it's going to say that's wrong because this is what w is equal to, right? We made up w. That's our invention. Your online homework system doesn't know what w is, right? It only knows about z. It wants to know what z is equal to, not what w is equal to. It doesn't even know that w exists. We invented that ourselves. So we need to find z. So what I need to do, since I'm done with w, is I need to bring z back into the picture. Right? So I'm going to take the w away, right? And what did w replace to begin with? It replaced log base 10 of z. So once you're done with w, you throw it away and put the old thing back in, right? The old thing that we replaced was log base 10 of z. We'll do the same thing on this one. So in place of this w, we're going to have log base 10 of z, and that's going to be equal to 2. And now we have to solve this for z. So we aren't even done. We still have to solve it for z. And so we're going to do the loop, right? It's a logarithm. It's an equation of a single logarithm. So we'll do the loop. We'll start with the base of the log, which is 10. Raise it to the power of 0 in this case. Set it equal to what's inside the logarithm, which is z. 10 to the 0 power is 1. So you get z is equal to 1. Do the same thing for the second equation over here. Start with the base of the log, which is 10. Raise it to the second power. Set it equal to z, which is inside the logarithm, and you get z is equal to 100. So it's a really clever equation. You have to solve it in this very clever way. And you get, I think, a pretty interesting set of solutions, 1 and 100. I don't know, it just seems like a pretty cool solution set. All right, so that is the equations part of section 4.4. We will look at the word problem part, hopefully in class on Wednesday. Thank you for watching this. If you have any questions, please send me an email, and I will see you soon.